So before we proceed to the actual design procedure of the flexural design of Prestressed concrete members, it is worthy to know and actually a requirement to be familiar with the different loading stages that are being experienced by a prestressed concrete element. So unlike the case of reinforced concrete members, the external dead load and partial live load are applied to the prestressed concrete member at varying concrete strengths at various loading stages. So for the case of reinforced concrete members, the loads, the ultimate loads that are anticipated to be carried by the member itself are applied usually at a specific concrete strength, which is actually the 28-day compressive strength of the concrete. So that is for the case of reinforced concrete members. But for the case of prestressed concrete members, the loads that are anticipated to be carried by the member itself, the dead load and the live loads, are actually applied uh, at the concrete element itself at varying concrete strengths, starting from the initial compressive strength up to the ultimate or the 28-day compressive strength of the concrete, as well as on the succeeding or the as well as the compressive strength of the concrete exceeding the 28-day compressive strength at various loading stages. So the first stage of loading that is being experienced by the prestressed concrete element is wherein the initial prestress force P sub I is applied. Then, at transfer, the force is transmitted from the prestressing strands to the concrete element itself. So if you can remember the the stages of prestressing that we have studied from the previous meetings, after after the hydraulic jack imparted a what we call jacking force to the prestressing reinforcement, it will be cut after the concrete already attained enough strength to resist the compressive force that will be later on transferred by the prestressing reinforcement. So after the prestressing reinforcement is cut, the tensile force that is imparted by the hydraulic jack will be experienced by the prestressing reinforcement all throughout its length. Thereby thereby it experiences a tensile force P, and usually that magnitude of tensile force P is what we call P sub I at transfer stage. So at transfer stage, this magnitude of tensile force being experienced by the pre-stressing reinforcement is transferred from it to the concrete element itself. So we know for a fact that uh, that magnitude of pre-stressing force P sub I is actually the final, the reduced force that is being experienced by the pre-stressing reinforcement at transfer after it experienced some magnitudes of pre-stress losses. If you can remember from our previous discussions. So if you will try to investigate what what are the total stresses that will act on the concrete element itself at this particular loading stage of the pre-stressed concrete, the stress diagram acting on the concrete element itself at this particular stage of loading of the pre-stressed concrete looks something like this. So this is actually the result of the stresses coming from the pre-stressing reinforcement, pre-stressing force P sub I. So this total stresses you are seeing here is actually the effect of the axial compressive strength, axial compressive stress plus the flexural stresses that is being induced due to the eccentricity of the pre-stressing force. So if you will try to sum up the stresses coming from that axial compressive stress and the flexural stresses coming from the eccentricity of the pre-stressing force, you will have a stress diagram that looks something like this. So this is actually the stresses due to the pre-stressing force alone. So that will be the resulting stress variation with respect to the concrete element. So after that stage, the full self-weight WDL or W sub DL acts on the member together with the initial pre-stressing force, provided that the member is simply supported, i.e. there is no intermediate support. So after this stage, wherein the pre-stressing force is transferred from the pre-stressing reinforcement to the concrete element itself, the concrete element itself will uh, will experience bending upward, or in other words, it will experience camber, uh, thereby making it look like a simply supported beam. And because of that, that forces the concrete element to support its own weight, W sub dl. So if you will try to investigate the total stresses that will now act on the concrete element after it already supported its own weight, the stress diagram will now look something like this. So you can see here the as the self weight is being carried by the concrete element, thereby producing flexural stresses, which has compressive stresses at the upper portion and tensile stresses at the lower portion of the concrete. The effect of those flexural stresses due to this application of load will make the stress diagram that will make the stress diagram look from this diagram to this diagram here. So that is the result of the application of the self-weight to the concrete element itself. So the next stage after that is the full superimposed dead load W sub SDL, including topping for composite action, is applied to the member. So in addition to the self-weight that is already being carried by the concrete element, additional load uh, will be carried by the concrete element. That will also induce flexural stresses that are actually compressive stresses on the upper zone, and the tensile stresses on the lower zone with respect to the neutral axis of the concrete element. So if you will now again add up those flexural stresses to this uh, current stress diagram acting on the concrete element itself, the diagram will now look something like this. So you can see here the variation of the stresses starting from the extreme top fiber to the extreme bottom fiber. So you can see here that the stresses on the extreme bottom fiber tends to have a lesser and lesser magnitude, while the stresses acting on the topmost fiber tends to have a larger magnitude of stress as we go along to the different loading of to the different loading stage of the pre-stressing operation. So you can notice that here on the corresponding diagrams that are being shown here. You can see here that as the loads are being applied to the concrete element, the stresses on the bottom fiber tends to have lesser magnitude, while the stresses acting on the top fiber tends to have a larger magnitude. And then after this particular stage, uh, most short-term losses in the pre-stressing force occur, leading to a reduced pre-stressing force PAO. So at this particular stage, the immediate elastic losses, which are the elastic shortening of concrete and anchorage seating and pressure loss for the case of post-tension elements, are now being experienced by the pre-stressing reinforcement, thereby producing a lesser magnitude of stresses coming from the pre-stressing force itself. So you can imagine that this magnitude of stress diagram here will now have a somehow lesser magnitude, since the magnitude of the pre-stressing force will now have a lesser value due to the occurrence of the short-term losses. Although in this particular diagram we did not alter the diagram itself, so just imagine that this diagram already diminish in magnitude with respect to the stresses that is acting on the concrete element. And then after that loading stage, the member is subjected to the full service load with long-term losses due to creep, shrinkage, and strand relaxation taking place and leading to a net pre-stressing force PE. So after that stage, additional loads will now be carried by the pre-stressing. By the additional load will now be carried by the concrete element, which will again produce flexural stresses on the concrete element, which has compressive stresses acting on the pre-compressed zone and tensile stresses acting on the pre-tension zone. And if you will add those flexural stresses to this current stress diagram here, the resulting diagram will now look something like this. So you can see here that the trend on the extreme bottom fiber, it tends to have lesser and lesser magnitude uh, until it became already a tensile stress. So from being a compressive stress, it tends to have a lesser and lesser magnitude until it reaches to have actually a tensile stress already. Just like what happened on the tensile stress here. So from being tensile, it experienced increase in magnitude. So from being tensile stress, it became a compressive stress that has now a larger and larger magnitude up to this particular stage of loading of the concrete element. And then after that loading stage, overloading of the member occurs under certain conditions up to the limit state at failure. So additional loads will be applied to the concrete element after this particular stage wherein it already supports the service loads that are intended to be carried by it. So the resulting stress diagram that will act on the concrete element after all of the loads that are anticipated to be carried by it already acted already acting on it will now look something like this. So this is actually uh, the stress diagram at failure at impending failure wherein the concrete element already experienced cracking because the stress here, since we know that this stress here tends to have lesser and lesser magnitude until it reaches a tensile stress already. After this stress here reaches the maximum tensile stress that can be experienced by the concrete element itself, it will now produce what we call cracks. So the cracks will now produce on the bottom part of the concrete element here, and because of that cracking, failure of the concrete will now occur. And uh, that small cracks can easily propagate to the upper portion of the concrete. So if the cracks already propagated on the upper portion of the concrete, meaning the tensile stresses acting on those particular part of the cross section already exceeded the maximum tensile stress that can be experienced by the concrete element itself. But because of the existence of steel reinforcements as well as the pre-stressing reinforcement, the tensile stress that are supposedly being carried by the concrete element will now be transferred from the concrete element to the steel reinforcement and the pre-stressing reinforcement themselves. So they will be the one now to resist those tensile stresses that cannot be resisted anymore by the concrete element because it already cracked and failed. It already broken up into two separate segments. So those tensile stresses will now be resisted by the pre-stressing reinforcement and the steel reinforcement themselves. And then together with that, the remaining portion of the concrete element will still resist the compressive stresses, which are here, which will we- which will act on the cross section of the concrete element together with the tensile force acting on the pre-stressing reinforcement and the steel reinforcement. So this is the stress diagram that will act on the concrete element at ultimate stage, at failure, at impending failure. So you can see here that from being linear, from the stress diagram, change from being linear to a somehow irregular shape here because at ultimate or at failure stage, the stresses acting on the concrete element is not anymore linear or not anymore linear. That's why it already became like this load diagram or stress diagram here, which has an irregular shape. So again, the total compressive stress coming from the concrete here at ultimate stage will be resisted by the tensile stress acting on the pre-stressing reinforcement and the steel reinforcements. So this will be the stress diagram at failure. So those are the different loading stages that are supposed to be carried or are supposed to be experienced by the pre-stressing pre-stressed concrete member as it supports the intended loads that are supposed to be carried by it.